it's working. Okay, and as we said, so we finished chapter 9 last time, and now we go to this chapter 10, the transform. Okay, so this is a bit of a sketching of what we are going to do, but let's start from the actual first page. So chapter 10 is the transform, and the transform is basically the discrete time counterpart of Laplace transform. Okay, so we are going to go over all those topics. Let's skim that very fast. Okay, and so those are the key concepts we will go through today. This is the transform. So we're going to do definition of the transform, and just like Laplace transform, we'll see that Fourier transform, this discrete time Fourier transform, is a special case of the transform. And then we have our ROC, and we have our pole zero plot. Okay, and we start with motivation. So motivation of the transform is just like the motivation of Laplace transform. So we said that back in chapter 3, we have this eigenvalue equation for our LTI system. We say that for any discrete LTI system, we have this kind of eigenvalue equation. So y of n equal to h of z to the n. So any complex is a complex power function z to the n is any of these functions z to the n is eigenfunction to any LTI system, with the eigenvalue being h to the z, and we calculated h to the z like this. Okay, so it's the summation from minus infinity to plus infinity, h of n times z to the minus n. And this is very similar to Laplace transform that we talked in chapter 9. So here we have a bit of comparison to Laplace transform here. Laplace transform was this integration minus infinity to plus infinity x of t times e to the st dt. And you see that this thing is basically the same, except that well, you have a summation here, and then you have integration here, and also you have z to the minus n, and then you have e to the minus st. But if you think z is e to the s, then this is z to the minus n is the same as e to the st minus st. And indeed this comparison between z and e to the s can explain most of the difference between the transform and the Laplace transform. So we kind of skip forward. So this is a picture I showed while I was setting up. So here is a schematic or a picture graphical way to show you that how to think about the transform as Laplace transform. Hopefully these don't confuse you too much. So here is what we think about, what we know about Laplace transform. We just spend a lot of time learning this Laplace transform, and we say that we have those ROC, we have those pole zero plot, and most of the time we deal with rational functions, so our ROC are bounded by those poles. And so maybe we have a pole and a minus one, and ROC are those straight strips. Okay, so ROC is maybe minus one to plus infinity, etc. Okay, and now in terms of a z transform, we are plotting on the z plane, right? So in Laplace transform, we are plotting against this s, and we have this real part of s and the imaginary part of s. Oh, sorry, I have those two. I need to fix this, but this real part should be sigma and the imaginary part should be omega. Sorry, I typed this wrong. Okay, I will update this, and I will fix this and upload the update later. Okay. Anyway, so S plane has a real part sigma and the imaginary part omega, and now we go to Z plane, and so now in terms of Z transform, we say we go to the Z plane, and the Z can be thought of as exponential of S. Okay, so this is still a complex number. S was an arbitrary complex number, and Z is still an arbitrary complex number. And now, but because of this exponential, so this straight line will become a circle on the plane. And to see this, then we kind of write z in polar coordinate. So z is some radius r times some angle omega. So is radius r times e to a j omega. And we think if S is sigma plus j omega, then we can equate this thing with this thing. You will see that this radius r is e to the sigma. So exponential of the real part of S, and omega will be just this omega. Okay. So, so if we try to translate from S plane to Z plane, then we are basically wrapping things around. So this imaginary axis omega will become this angle omega, and this real axis sigma will be the radius here. Okay. And so this j omega axis will corresponding to sigma equal to 0, which equal to r equal to 1. And an important thing here is an important thing is that omega now going from only 0 to 2 pi, because omega comes in circle, right? And this is an important feature that we keep talking about. That is when your signal is discrete time. Okay, so now we have the discrete time signal h of n. Now, then we go to the frequency domain, or now in the z domain, then this omega will be periodic with period 2 pi. So you can see that this picture, in this picture, this is very intrinsic. So omega go from 0 to 2 pi, then you go back to the same point. And this is kind of the reason why we want to take this exponential of S, because in S plane, this omega, well, omega can come from minus infinity to plus infinity. They all look like a different omega. But in a Z plane, because you do this exponential, then omega automatically has this period of 2 pi, because then you add omega by some 2 pi, then you go to the same plane. And algebraically, it's this equation. So e to the j omega plus 2 pi times n equal to e to the j omega n. Okay? And yeah, so this is the thing we keep talking about. If you are discrete, if your signal is discrete time, then in the frequency domain, your signal is periodic with period 2 pi. And hopefully I can express this. So I like to think this kind of topologically, like you try to wrap this whole thing into a circle to transform from S plane to Z plane. So you have this, say you have this boundary of your ROC. It was a straight line in the S plane, and now you Z transform to to Z plane. Then you kind of wrap this straight line into a circle, and with a periodic of 2 pi. So every 2 pi period, you wrap back to the same point of the circle. Okay. And for example, this j omega axis, the j omega axis will wrap into this circle here. Okay, so you're kind of stretching your whole strip of ROC into rings. Okay, now we don't see a ring because the ROC extends to infinity, but you can think about. So we're going to see an example where in the Laplace transform you will see something like a ring, like a strip, and then in this transform you have ROCP rings. Okay, so this is a bit of intuition about the transform, and we actually spoiled a lot of the intuition we're going to cover today or next week. And hopefully this is not too fast. And any questions so far? Okay. If not, then we know this is what's going to happen. Then we go to detail of derivation of some properties about this transform. Okay. And as we say, so we motivate by this chapter 3 eigenvalue equation as Z transform, and now we just define Z transform as this big X of Z equal to summation small x of Z times small z to the minus n. Okay. And so this is a generalization of a complex Fourier transform. So sorry, discrete time Fourier transform. So back when we do discrete time Fourier transform, this Z was e to the j omega. But now it's just Z, okay? And now Z don't need to be e to the j omega, Z can be any complex variable, okay? And then by notation, we say this thing is big Z of x of n, okay? And so, and we have bijection relation, we written as this. So we have some x of n and equal z transform to some big X of z. And now we see this relation to Fourier transform. And as we just did, so we can express this small z as a polar coordinate. So small z as r e to the j omega. Then we see that big X of r times e to the j omega. So we just express this as z back into this equation. Then we have x times r e to the j omega times e to the j omega times to the minus n power. Then we separate it into two parts. Then we have and we combine this r to the minus n part, and we have e to the j omega minus n part left. Okay? And so we group this thing together and times it, and with h e to the minus j omega n left. Then we see that this thing is the Fourier transform of x of n times r to the minus n. So we have done the similar we've done similar derivation before. So we see that back in Laplace transform, we say that Laplace transform was equal to Fourier transform for each sigma. Laplace transform equal to Fourier transform of some function. And now we have a similar result. We have that we fix an r, then the z transform equal to the discrete time Fourier transform of some function of r. Okay, so yeah, this is just the Fourier transform. Fourier transform is summation n your function times e to the minus j omega n. Okay, and yeah, indeed we say this is this big X of r e to the j omega is the Fourier transform of x of n times r to the minus n. Okay. And also, as we said, when we set r equal to 1, which corresponds to sigma equal to 0, then our thing reduces to Fourier transform. Okay. So we see that our z transform, x of z setting, if we fix ourselves to z equal to e to the j omega, then it's exactly this big X of e to the j omega, which is a Fourier transform of x of n. And this also tells us that why we have this funny notation for Fourier transform of discrete time signal. Okay, so back in chapter 5, this looks really weird because we have a function of omega, but we write it as a big X of e to the j omega, and now we see a reason why we write it as e to the x of e to the j omega instead of x of omega, because we like to think this as a special case of z. This is e to the j omega is restricting restricting z to e to the j omega. And yeah, so in a picture, you look at this. So we have this z plane, the real axis, imaginary axis, and we have this important unit circle. And we think the z transform happening on this unit circle are the Fourier transform of your signal. Okay. And yeah, so you have a different omega corresponding to this circle with different angle omega. Okay, and yeah, so yeah, as we said, and this circle is called the unit circle because it's a circle of length 1, and this unit circle name is kind of important just because we are going to keep saying this name. Okay. So unit circle is just it's a circle with radius 1. Okay, this is quite similar to Laplace transform. So hopefully everyone is okay with this. Okay, if we're okay, then we keep parallelizing we keep repeating what we do in Laplace transform. And now we start with this first example that is the z transform of the most basic signal, that is our exponential decay signal. So we have our x of n equal to a to the n u of n. Okay. And if absolute value of a is less than 1, then we have an exponential decaying signal. And it is a signal that cut off at n equal to 0. Okay. And we calculate its z transform directly by the definition. So big X of z is summation is x of n, which is equal to a to the n u of n times z to the minus n. Okay. And this u of n will just cut off your summation from n to n from 0. So we have n from 0 to infinity, and we see that we have a to the n, z to the minus n. So we can combine those two things to be a times z to the minus 1 to the n. So this is a very nice geometric series. Okay. And okay, so geometric series, we can use a geometric series formula to calculate, but we need to be a bit careful because sometimes this geometric series will diverge. Okay. And now we go back to the concept of ROC. So we need to think about what kind of z will make this geometric series converge. Okay. So we want this summation to converge, then basically what we need is that we need this series to converge, and what we need is the absolute value of this this thing here, this a to the minus 1 should be less than 1. Okay. If the absolute value is less than 1, then the series will be convergent. Otherwise, it will not be convergent. Okay. This is something we get from basic calculus. Okay. So we need absolute value of z minus 1 to be less than 1. This analysis is a bit more complicated because a and z are complex value. But you can go to calculus to see that you need az minus 1 to be absolute value to be less than 1 for this summation to be convergent. Okay. And they move things around. This means that the absolute value of z need to be greater than absolute value of a. Okay. And when absolute value of z is greater than absolute value of a, then we have a geometric convergence geometric series here. And so if we call this r, then the result is 1 over 1 minus r. And r is az minus 1. So we have 1 over 1 minus az minus 1. And if we want to express this as a as a rational function of z, then we multiply z on both upper side and the lower side, so we get z over z minus a. Okay. And so this is z transform of our exponential function. It's z over z minus a with absolute value of z greater than absolute value of a. Okay. So this is a direct comparison to our example 9.1, where we had Laplace transform of the exponential decay function, and it was 1 over s plus a. Okay. And anyway, so we have our z transform of our basic function. Okay, it's this z transform, this a to n u of n is z over z minus a. And unfortunately, this is more complicated than what we get from Laplace transform, because we have uppercase z and also lowercase z. So this thing both has 0 and has a pole. Okay. And anyway, so here this thing both has a 0 and has a pole. So it has a 0 at a 0 and a pole at a minus a. Okay. So somehow this exponentiation of so the exponentiation of s make the function more complicated, and this is just what happened, and this will make our inverse z transform to be more complicated too. Okay, but that's for next week. For now, we have this z transform, and we can plot the ROC like this. So so we have pole at A, and ROC will be those absolute value of those z with absolute value greater than absolute value of A. So we have a kind of a circle with absolute value of A here, with radius being absolute value of A here, and the ROC will be all the z outside of it. And it has a pole here, and it also has a 0 in the middle. Okay. And it's a bit confusing because it has 0 outside of ROC, but this is what happened. Okay. And any question? And I guess also here we can see we can kind of analyze whether the Fourier transform exists or not by seeing whether the ROC include a unit circle, and we see that that checks out with our intuition. So here we have here we have a between 0 and 1, and when a is between 0 and 1, then we have an exponential decaying function. So its Fourier transform exists. And when a is greater than 1, then we see the ROC will be outside this unit circle. Then the ROC will not include a unit circle, and the Fourier transform does not exist. And that's because your a to the n u of n is an exponential growing function, and it should not have a Fourier transform. Okay. And so this is the transform of exponential function. And now we go to example 10.2, and this is still parallel to what we do in Laplace transform. So now we have this left-sided exponential decay function. We have this x of n equal to minus a to the n u of minus n minus 1. And to save you some calculations, so we think about what kind of n will be included in this u of minus n minus 1. Then you want the minus n minus 1 to be greater or equal to 0, and so you move this minus n to right hand side, you have minus 1 is greater or equal to n. So this thing has value only when n is less or equal to minus 1. And when a is greater than 1, then your signal look kind of like this. Okay. And anyway, so we have this kind of weird left-sided exponential function, and we can calculate its big X over z also. So we do once again we use the formula of big X over z. It is summation x over n, so we have minus sign here, and a to n here, u of minus n minus 1 times z to n from definition of big X of z. And then is u of minus n minus 1, as we say, we'll keep all the n as less than equal to minus 1. So our summation now change from minus infinity to plus infinity to minus infinity to minus 1. Then we do a change of variable, so we change n to minus n. So this n from minus infinity to plus minus infinity to minus 1 become 1 to plus infinity, and then this n got a minus sign, and this minus n become plus n. And finally, we change the range a little bit because we want to do geometric series sum formula a bit nicer. So we add, so we add a extra term of n equal to 0. So this was n from 1. Now we sum from n from 0. And because we get an extra term, and the n equal to 0 term will be 1, so it was subtracting, this was negative, so we add back this n equal to 0 term. Okay, so this is just a little mathematical trick for this to be a bit simpler. Okay, and now once again for convergence, we want this absolute value of a to the minus 1z to be less than 1. And then we move this around as the equation for z. We see that we want absolute value of z to be less than absolute value of a. Okay, so the region of convergence will be this absolute value of z less than absolute value of a. And the algebraic part will be 1 minus 1 over the 1 minus this summation. The summation will be 1 over 1 minus this number here, this expression here, so a minus 1z. Okay, and then we do the calculation. Yeah, and then we do excuse me. Then we try we calculate all these things. Then we see that the algebraic part is once again z over z minus a. Okay, so this is same as the example 10.1, except that its ROC is different. So ROC will be this absolute value of z less than absolute value of a. Okay, so this is in parallel of what we have in chapter 9, where we get two different time domain functions that z transform to the same algebraic expression, but they have two different ROC. Okay, so now ROC look like this. And then it's pole and 0 are the same. So we have 0 at z equal to 0 and pole at a. Okay. Any questions so far? Okay. Yeah, so this is the ROC of our second signal. So it has the same algebraic part, but the ROC will be inside this radius of A. Okay, and now we go to the third example that's more complicated. So we have two of those exponential decay signal linear combined with each other. So we have 7 times is 1 over 3 to the n u of n minus 6 is 1 over 2 to the n u of n. And once again, we can do the calculation of this z transform. And this will turn into two geometric series. This is summation 1 over 3 z to the minus 1 to the n. And this is summation 1 over 2 z to the minus 1 to the n. And for this to be convergent, basically we want both those two summations to be convergent. Okay, and if both of them are convergent, then we get this complicated expression. So 7 over y minus 1 over 3 z minus 1 minus 6 over y minus 1 over 2 z minus 1. Okay, and then we can calculate this out as a rational function of z minus 1. So we have a whole bunch of z minus 1, and then this can be expressed as a rational function of z, like this. Okay. And as we say, we want both of these to be convergent. Then we want absolute value of this thing to be less than 1, and absolute value of this thing to be less than 1. So absolute value of 1 over 3z to the minus 1 to be less than 1. Absolute value of 1 over 2z to the minus 1 to be less than 1. So absolute value of z needs to be greater or equal to 1/3 and 1/2. And together, we should pick the most strict condition. So the ROC will be z greater than 1/2. And we can also do this by just use linearity of z transform. And we have seen that both of those exponential decay in turn is a special case of example 9.1. So sorry, 10.1. So this will be transformed to this 1 over 1 minus az minus 1, where a is 1/3, and this transformed to 1 over 1 minus 1 over 2z minus 1. A is 1 over 2, and yeah, so we will transform to this. And then the ROC of this will be greater than 1/3, ROC of this will be greater than 1/2, and together the ROC is basically an intersection, because this is an easy example. But as we know, as we learn in Laplace transform, this linear combination can have the ROC increasing, because sometimes it will cancel the pole. But here the pole doesn't cancel, and we have ROC greater than 1/3, ROC greater than 2/3. And here we have the ROC just being the intersection of those two ROC. Okay, and we see a more complicated example. So now we have this example of x of n being exponential decay times some psi. Okay. So those are exponential function times some psi. So we have sine pi n over 4 here, and here we have exponential, and here we have another exponential with complex number here. So here we have exponential with a equal to e to the j pi over 4 divided by 3, and here we have exponential of e to the I confused myself. So our function was this. So we have exponential 1/3 times psi. And then we can just use inverse Euler to break the sign into the linear combination of two exponential. So this sine pi n over 4 become 1 over 2j e to the j pi n over 4 and minus 1 over 2j e to the minus j pi n over 4. And those j pi n become e to the j pi n become e to the j pi to the n, etc. Okay, so we break this sign function into complex exponential, and now once again we just have two exponential function on n, and once again we do this transform, and we can just use a geometric series sum to calculate those two terms, and or we can just use example 10.1 with complex a here. So we have a equal to 1 over 3 e to the j pi over 4. And we have a equal to 1 over 3 e to the minus j pi over 4 here. And we just have a linear combination. Okay, so the algebraic part is really easy. So it's a very dirty expression, but you can calculate it, and you can and we can clean it up as a rational function of z, and you will look at this. It's quite complicated. It's 1 over 3 square root z over z minus 1 over 3 e to the j pi over 4 times z minus 1 over 3 e to the minus j pi over 4. And so this is the algebraic part. It's quite complicated, but really straightforward. And the bit more complicated part is the ROC of this thing. So the ROC, we want basically the intersection of ROC of this part and this part. And the ROC of this part will be z greater or equal to this a here, absolute value of this a here, and z greater or equal to absolute value of this a here. But the absolute value of those two things are both 1 over 3. So the ROC is just z greater than 1 over 3, and we have our pole 0 plot here. And once again, we have a 0 at 0, and we have now these two complex poles, two complex pole at 1 over 3 e to the j pi over 4, and 1 over 3 e to the minus j pi over 4. And as we say, ROC is greater or equal to minus 3. Okay, any question so far? If not, then now we summarize some properties of the ROC of the transform. Okay, and now we so ROC, so the property we actually get one extra property. We have now 10 property of ROC of the Z transform. Okay, and anyway, but most of them are very similar to what we have in Laplace transform. And so first property, similar to Laplace transform, we have that ROC of x of z consists of rings in z plane centered around origin. Okay, so this was just what we said here. So compared to Laplace transform, so Laplace transform, we say ROC consists of strips in the x-plane, and we kind of loop those strips together into rings. So now in z-plane, we have the ROC being being consists of rings in the z-plane. Okay. And so the derivation is exactly the same. So so we say that the Fourier transform for discrete signal either exists or doesn't exist for every omega. Okay, so either the whole ring is inside ROC or not. Okay, and then with this, because we think the Fourier transform only exists for the full ring or not, so the ROC of the Z transform will also consist of rings. Okay, and also then we get this property 1.5 that directly tell you whether some radius will be inside ROC or not. That is, we can just check whether the signal x to the x is the absolute value of x times r to the minus n is absolutely summable or not. Okay, this x of n R to the minus n is absolutely summable or not will determine whether R is inside ROC. Okay. Okay, so the value of z where x of n R to the minus n is absolutely summable. And so the idea is kind of like this. So we have some radius R, this radius R ring, we want to see whether it's inside ROC. And it's inside ROC means that Fourier transform of Fourier transform of x times R to the minus n converge. And and that will correspond to x of n R to the minus n is absolutely summable. Okay. And I think yeah, this is one of the three delicious. Yeah. I think. Yeah. So this is why this is why this is true. Okay. So just like in Laplace transform. So we have this property 1.5 says that some radius R is inside ROC if only if x times R to the minus n is absolutely summable. Okay, so this is property 1. And property 2 is also exactly same as Laplace transform. And they just say ROC does not contain any pole, and I think this is very obvious because at the poles your x of z go to infinity, and by definition is not convergent. Okay. And now property 3 we have something a bit different. Okay, so property 3 says that if x is finite duration, so x is starting from some value n1 and stop at some value n2, and then ROC will be entire z plane. So far it's the same, but we have a weird exception here. So we accept z equal to 0 and or z equal to infinity. Okay. And so this is quite different from our analysis in this is quite different from our expression in in Laplace transform. Laplace transform we don't particularly care about what happens in infinity, but here this entire z plane can or ROC being entire z plane, but can still have something weird happen at z equal to 0 or z equal to infinity. And yeah, z equal, I guess a bit about intuition. So the infinity was infinity, and when infinity happen with weird thing happen is fine, makes sense. And but z equal to 0 now it also correspond to an infinity at S plane, because you think about now back to this. If we think about what is z equal to 0 corresponding to S plane, and that was actually sigma to negative infinity. Okay, so z equal to 0 and z equal to, and similarly z equal to infinity correspond to S plane being sigma equal to plus infinity. Okay, so what I want to say is just that z equal to 0 and z equal to infinity are both infinity point at S plane, and so weird thing will happen. Okay, and let's see what happened to. Okay, so let's go back a little bit. So first the easy part. So if the x of n is finite duration, then for finite z, our big X over z will be convergent, because you can just look at this equation and see that well, for finite z you are summing over a finite number of terms, then you just get a finite number here. Okay. So this is quite straightforward derivation. Now we need to think about what happened at z equal to 0 and z equal to infinity. And our big X of z is the summation n1 to n2 x of n z to the minus n. Okay. And so what happened is when z go to infinity, then well z will go to infinity, and when when z go to 0, then 1 over z will go to infinity. That's why the 0 and the infinity points are weird. Okay, and I guess let's look at this 0 point first. Okay, so so this 0 point, excuse me, this 0 point will make 1 over z go to infinity. So all the negative power of z will go to infinity. Okay, and that means that if you want your RC to contain 0, then you cannot, then this summation cannot have a negative power of z. Okay, if you want RC to contain 0, where 0 means 1 over z go to infinity, then this summation should not have negative power of z. And so that only happen when your summation range kind of look at this. So your n2 should be less or equal to 0. That's when this summation don't have a positive number of z. Sorry, don't have a positive number of n, which means a negative power of z. Okay, and so we have our property 3.5.1, which says that the RC contains this 0 if only if n2 is less or equal to 0. Okay, so in this case, will contain RC will contain z equal to 0. And similarly, when z goes to infinity, so what's blow up is those positive power of z, and that positive power of z is the negative power of n. So if you want your RC to include infinity, this summation here should not have a negative power of n, and that means you want your n1 to be greater or equal to 0. Okay, and this is so this is a condition for your RC to contain infinity, and you can kind of see from those conditions, because n1 need to be less than n2, so you cannot contain both the 0 and the infinity. You can either contain 0 or you can contain infinity with those two things, with these two possible conditions. Okay, so this is HR analysis from on top of what we have in Laplace transform. Laplace transform, we just say if finite duration signal, then our RC is entire S-plane. But in this Z transform, we see that our finite duration signal, RC will be entire Z-plane, but we need to analyze the infinity, z equal to 0, and the infinity carefully. Okay, and yeah, you want to include 0, then your n2 need to be less or equal to 0. Want to include infinity, our n1 need to be greater or equal to 0. And that's the example of this property in action. And I guess I lied. So we actually have a way to have both of those achieved. Okay, and that's this example. Okay, so our example is a delta function, delta of n, where n1 and n2 both equal to 0. Okay, so this is the only function that satisfy the both property. That's when both n1 and n2 is 0, and we have this delta of n. Okay, our signal is delta of n, and the Z transform is very simple. So delta of n Z transform, we have this summation delta of n Z to the minus n, and as we know from the shifting property of delta function, this will pick out the summation to be n just equal to 0. So we have Z to the 0 is just 1. So delta of n Z transform to just this constant function 1. Okay. And just from this result, you see that this should be convergent for every z, because these don't even depend on z. For every z, 1 is 1. Okay, no matter what your z is. Okay, so this is convergent on every z, both 0 and infinity. Okay. Okay, and we should see that is checked out with what do we see? So we know, so it's a finite duration signal, so it's so the RC entire Z plane, and at 0 we see that n2 is 0, so n2 is less than equal to 0, so RC contain 0, and also n1 is also 0, so n1 is also 0, so our C will contain infinity. So this delta of n satisfies all the properties, it contains everything inside its ROC. Okay, and now we see another signal that is this impulse signal delayed a little bit. So we have our delay unit impulse delta of n minus 1. And delta of n minus 1 will be transformed to, well, now we pick our n equal to 1, so we have z of minus 1. Okay. So now the transform is z of minus 1, and we see that this is convergent everywhere for every z except when z equals to 0, because when z equals to 0, we have 1 over 0 become infinity. And z equals 0, there is a pole. So our C is the entire z plane, including infinity, but not z equal to 0. And we check those two properties. And so now both n2 and n1 are equal to 1. And we see that then only this property 3.5.2 satisfy, and now this doesn't satisfy. So the ROC for delta n minus 1 doesn't include 0, but include infinity. Okay, and similarly now we consider delta of n plus 1, and now the z transform will be z because you pick n equal to minus 1, and z to the minus 1 equal to z. And our C will be everything finite z, and obviously when z go to infinity, z equal to infinity. Okay, so our C is every entire z plane, including z equal to 0, but not including infinity. And once again, we check those two properties. We see that because now n1 and n2 equal to minus 1, so this 3.5.1 is satisfied, n2 is less equal to 0, but now n1 is not greater equal to 0, so we don't include infinity as our ROC. Okay, and we have 1 minute, but I think we can stop now, and next time we'll see more properties of the transform, and we're going to see those right-sided function, left-sided function, etc. And there will be more analysis about whether 0 or infinity is inside your ROC of the transform. Okay, so yeah, see you next Monday, and we'll continue on our the transform.